So, uh, it's April 15th. Hi, welcome. Yes, definitely. Woo, there I am. Your task, we just finished up 2 Zoom classes. I had one at 10 and I had one at 2. We went over both of the videos and how to do them. I wanted to show you really quickly how quick it goes. So remember, you're going to find access to the video analysis app by going into Classroom. Ooh, yeah, I should say that. All right, going into Classroom and finding the link if you haven't bookmarked it already. So it's an app. It lives on Chrome. So that means you can go to any web browser and locate it. But as long as you have access to Google Classroom, you should be able to get access to it. It's cool stuff. So the first one was that we can do this positive velocity video. And so we're going to load that one up right now. All right. Okay. Ha! There we are. All right. First things first. It looks like I'm a teacher. I would know when something's kind of off. The camera looks like it's a little bit, so I want to kind of fix that. It doesn't matter what order you do this in. You can do this in any order you want. You can add points now. You can do that stuff. But the first thing, let's play it. Let's just watch it, see what happens. Okay, someone pushes it. All right, I'm seeing the video doing some weird stuff. I'm not sure what that is. I'm going to see, did the cart really go backwards or is it just moving forward? And internet's doing some fun stuff. So I'm clicking forward. Oh, there's the finger. It pushes it along. It doesn't seem like it's changing direction or anything. It's going along that line. So, cool beans. I want to pull it back to where it's free of any other influences. Right now, it's got the track and it's got Earth. Those two things are acting on it. So we don't want the finger because that's going to change the type of motion that we have. We want it to see where it goes. Looks like since I'm highlighted on the ball, I can use the arrow keys to kind of scrub forward frame by frame. And let it load, Mr. Quiroz, let it load. All right. Okay. There I can see clearly that the finger is not touching the back. Awesome. Now, next thing is I'm going to set my scale. All right. I'm going to take care of the origin first. It looks like this ramp is at an angle. So I'm going to click on this x-axis and just drag it so it's lined up with that track. Cool. That's something new. They were talking about adding that, and they just did. So that's awesome. And I'm going to move this anywhere I want. Notice I moved it way above the track. I kind of want it out of the way for now. The cool thing is I'm not trying to predict where this cart is going. I just want to know if I'm right about, I think it's going at a constant pace. So I want to know if I'm right. I would see something happen. So I've lined up my scale. Okay, cool, as best I can. I can turn that off when I go back to add. All right, there's high contrast here where that tape is, and I could start there. However, I wouldn't want to have to click 200 times. There's 226 frames. I mean, not 200, it'd be like 100 and something frames, but I don't want 100 points of data. So if we have that much data, think how many times does 20 go into what we have left there? About 7 times. So maybe we can skip every 10 frames. So we click on this and choose 10 frames. We can always go back and choose 5 frames and get more data, but we might be satisfied with 10. I know I said 5, but looking at this now, it seems like 10 will go a lot quicker. So if I click on that, it automatically moves forward. I just click on the same exact spot over and over again as I find it. There. I'm not going to click on it now because it's different than it was before. It's a different type of motion at that end. There's like a beginning, a middle, and an end there. I want the middle where all the fun stuff happens. Well, some could argue that the fun stuff at the end and crashing and me getting to push a cart, yeah, that's fun too. Okay, so now I'm ready. Which axis looks like which dots look like they're doing something in the position and time graph? It looks like the x-axis is doing something. Let me go back to my origin and I can show you that we really can do anything with that origin. It's pretty cool. So I go to my scale. If I move this around, I notice those blue dots will move too. And my red dots really don't change angle. That's good. So you can see it really doesn't matter where I put this. It'll just shift where the red dots start, but the angle it is the same. Kind of cool. Okay, so I'm ready to go. I can look back and see if there's any points that feel like they're out of pace, but even if I look at these trails, they're evenly paced in the same amount of time between them. This is going at a constant rate, so that's evidence for sure. Now, I can turn off the y-axis because it's not doing anything in the position time graph. Cool. I'm going to go to my graphs and choose, get rid of the video, get my two graphs going. There we are. And oh, my velocity graph looks okay too. I'm going to get rid of the y velocity since it's at 0 pretty much the whole time. And then that happens. Ah! Okay. My data is all messed up. Okay, wait a minute. If you seriously look at it, this point over here, right there, that's at 0.26 something. And then this point over here, that point is at 0.265. That's like off by a millimeter per second. Really? Okay, this is where you go into graph options. Always make sure your 0 is shown for the motion axis, the position axis, or in this case, the velocity axis. The time axis, 0 is going to be there because we start at 0, sure. But we can always have different opinions on that too. But if we go into graph options, we can choose our everything was positive. Maybe I choose a small negative number like negative 0.1. And I choose maybe double that other one number like 0.5 just to get a kind of clear perspective. And wow, look at that. It looks pretty flat. I would expect a velocity to not change, constant velocity, not changing. That should be flat. Cool. I'm going to go ahead and do my curve fits. Yeah. Curve fit. Apply. 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 A curve fit. Holy moly, it looks pretty flat. And that slope, wow, look at that slope. That slope is basically 0. All right, cool. So my friend on the iPad will help us out with that stuff. So that means we have something kind of cool. We have motion position model, and we have a velocity model for all motion that we've studied so far. So for position will be equal to 3 terms. 1/2 acceleration times time squared. That's how much displacement happens based on it accelerating, changing its velocity. And then this next one is how much it's going to go already because it already has a speed of velocity. Plus, where did it start? So now we can actually figure out where it's at. Okay, for velocity final is going to be based on the acceleration times time, how much velocity changed in that much time, and then where did it come from? Where did it start at? So we know what our final velocity is. Those are it. Those are our 2 motion equations. We change them as we need to. Now, here we just saw that the motion graph was a straight line for position time. Something like that. All right. We had an M, we had a B, and that was it. So if we think about it, we had something like this. Position is equal to, if I go back to my screen and take a look over there, it says X is mx plus b. I got X equals 0.2582 times T plus negative 0.5014. Okay, what does that mean? Well, if I look at my format here, this is a number all by itself. This looks like that. This has no component. Wait. So, oh yeah, wait a minute. If A is 0, that goes away. Okay, my initial velocity is the same velocity the whole time. It's 0.2582. What units? Well, this was meters and this was seconds, right? Time in seconds and position in meters. So that means that this is 0.2582 meters per second. That's my initial velocity. And my initial position, which I didn't ask for, but the initial position is arbitrary. In my case, it was 0.5014. In your case, it might be different. And it's position, which has the units of meters. So there it is, my meter. All right, there's my information. Oh, let's look at the velocity time graph really quick. All right, I'm saying right now that the acceleration should be 0 meters per second squared because it's constant velocity. Well, look, the slope of the velocity time graph is the acceleration. So I have a velocity graph that looks like this. The slope of that is 0, isn't it? That's the same thing. So I'm also looking at this model, and it says, hey, velocity equals acceleration times time plus initial. Well, acceleration is 0.000, yeah, it's pretty much 0. That goes away. And then 0.2591. Very cool. So this is my B value. It's in meters per second. Look at this number and this number here. They both agree to the hundredths place. So basically, I could stay there. So it's 0.26, or I can say it's 0.258. Or 0.259, I'd be right either way. But the idea is I should be able to see your graph and I see you came up with that and that you have units on it. Brilliant. And the acceleration was 0. All right, cool. So there's that. What about the other one? Well, that's easy. We just do the same thing for the other one. All right. So I switch back out of this. Next. Loading. Load that video, loading. So, again, we're going to go through our common things. Set an origin. Okay, cool. I'm going to play the video too. I think I see him holding a ball up there, and it's going to come down here. I'm going to put this down here. Does it matter where you put it? No. Does it look like it's going to fall straight down? Yep. Do we need to change the angle of this? Nope. Okay, cool. It looks like all my motion is going to be in the y-axis. I'm going to play this video just to kind of see. Okay, it's doing some weird scrubbing stuff, but I can see that the ball is kind of close together at the top and then far at the bottom as it goes down. It's speeding up as it falls, as most things do when you drop them, right? So another thing, I'm going to look at this and it says, whoa, there's only 44 frames here. Well, I don't want 44 points of data, so maybe I go every other frame, and if I need more data, I will. But right now, I need to figure out where that is. Next thing, I'm going to find out where this feels good at. They look like they use Post-it notes or stickies to be able to help us see that better. But if you're careful enough, you can get it there and feel good about it. You can always come back and change this to see how it might change your values. But within reason, you kind of want to set it and forget it. And now I'm ready to add points, but I can't add on the first frame, I don't think. I'm going to go for it, and it looks like he's not holding it, but it's super blurry. I can't tell. It looks like he's not holding it, but he might still be. So maybe I'm going to go one more frame to see where it is free from him and completely just in control by gravity. So force of gravity, it didn't look like it changed much there. Oh, it did fall down a little bit, but it's definitely not touching his hands now. I see space on both sides. Okay, I think. I can't really tell, but that's something you can talk about. Like, well, we were off a little bit because, well, we couldn't see it. All right. So now I'm going to go to my settings down here. And because there's only 44 frames, if I skipped every 5 frames, I'd only get like 8 data points. I need more than that. So I'm going to go 2. All right. 10 to 20 when you're doing video analysis. The more data, the better, usually, as long as it's the motion that you care about, not the beginning, the middle, or the end, whichever, not all of it, which one you care. Are you caring about the beginning? Are you caring about the middle? Are you caring about the end? Here, the story is about the middle. It's all about the fall. So that's what we're going to track. All right. So in this case, I'm going to turn off trails because the points are going to get so close together that it's going to be hard to see where they are. So I'm going to go up here and I'm going to use the top of the ball. I'm just going to click and it's going to move. It's going to click and it's going to move. And knock this out. Bam! And I keep moving forward. And I don't feel comfortable clicking that spot because that's like the last frame and it's in contact with the ground for sure. So it's probably going to change things. So I'm not going to click on it. Now, ooh, this graph is awesome. Oh, let me go back and turn on my trails and I can confirm. Up here, looking up here, come on. Right up here, you guys see it's kind of like spacing is really, really small. And if I look down here, the spacing is larger. Remember, the dots are spaced evenly in time. So this is the same amount of time as it was up there. So it's interesting. And you can see all the motion is vertical. So in this case, I don't want the X, I want the Y. So I'm going to get rid of the I want to get rid of the X because it's not doing anything. There's no left and right motion. All right, cool. Now I'm going to turn off that video and go to graphs. Turn on my two graphs because I want position and I want velocity. I want to absolutely show you that, yes, this is absolutely right. Look at that. X velocity is not doing anything. Well, that's because it wasn't. It wasn't moving left or right. That makes sense. It was moving only up and down. There we go. Ooh, pretty. Something you can do is kind of zoom out of your graph a little bit. It's a little technique I learned to be able to see the shapes of these things because sometimes when you're zoomed in so close, you can't tell what's going on. Let's say if I put 10 seconds for the x-axis range. Does that look like a parabola? I think so. It's way, like I can see that it's like arced. It's pretty good. So I'm going to go back to zoom all data again so it's lined up and click back this, do my curve fit. Linear is not going to cut it. The only other one I have in my toolbox right now is quadratic. Don't choose anything else. Don't be silly. Okay, check that out. I'm off by my units in meters. RMSE is 0.01. I'm off by 1 centimeter. Remember, the meter stick was like itty bitty in the video, so being off by 1 centimeter, you can't even see a centimeter on the video. That's how crazy that is. Okay. I think it was like 49 pixels or something was the meter, which means that a centimeter is less than a pixel. So I like it. All right. I'm going to do the same thing with the velocity graph. It looks like a straight line. This is conclusive to me. Say that this was constant acceleration. This object was undergoing constant acceleration. It was getting faster and faster as it fell. And it fell from really, really slow speed. It fell from rest, but I don't think we caught it because it was already moving when we started clicking on it and his hands were off the ball. So whoop-de-doo. I'm going to apply that curve fit, do my linear. I don't see my zero axis, so I'm going to go in here and just kind of make it sure it happens. I'm also noticing all my numbers are negative, so my zero axis should be above me here. Okay. If I look at my graph options, oh yeah, look at that. The bottom is negative 13. What if I made the top like, I don't know, 10? Or maybe 5. Ah, now I can see that line there. There it is. Yeah, maybe 5 is too much because it seems like my data got squished. So I'm going to choose like 1, something so I can see that data. So I'm going to go over here and go like, oh, 1. Yeah, now my data takes up most of the graph. I can see here, pretty cool. My velocity time graph is a negative slope. It's constant slope, which means my acceleration is constant. What is my acceleration? Well, remember the model. If I go back to my crazy stuff here. Okay, so there we had those models. Well, I have 2 graphs, 2 curves. I'm going to go take a look at those. If I look at my values here, I'm going to go over here and get rid of my data table so it's a little bit easier to see. But the idea is I've got information up here and information down here, and they should agree with each other. So let's see. I have the quadratic equation, which is ax squared plus bx plus c, and my a is negative 4.454, and my b is negative 1.084, and my c is 9.388. Incidentally, that building must be it was released at 9.4 meters above the ground. Cool. I know the height of the building roughly now. All right. If I look at this is this term right there, this is this term, and this is this term. So be careful. My acceleration isn't negative 4.4. My acceleration is double that, because 1/2 acceleration is equal to negative 4.454 meters per second squared. So I double that, and I get negative 8.908 meters per second squared. Do I see that anywhere else? If I look at my velocity graph, my slope is really close to that. The slope of the velocity graph is acceleration. There it is. My m is negative 8.683. So negative 8.683. I can see that my two graphs don't really agree exactly, but they're dang close. Look at this. This number is where they disagree. So if I round it, that's negative 8.7. This one's negative 8.9. I feel like my acceleration is like negative 8.8 meters per second squared. My initial velocity. My initial velocity on the y-axis is the y-intercept on the velocity graph down below, negative 1.232. Up above, it's my b value there too. It's negative 1.084. Oh, those numbers kind of agree with all the way to the 1st place, or 10th place, excuse me. So I'm looking at that and saying my initial velocity looks like to be negative 1.1 or negative 1.2, but you see that they don't differ that much. So, we're talking about 10 centimeters a second that is different, and we could barely see a centimeter on there. So that's really good. I'm done. I just got to do screenshots and talk about my stuff, and I'm good to go. Hopefully video analysis gets faster and faster for you guys. Thanks so much. I will see you on the flip side. I will have more Zoom meetings scheduled. Right now I'm moving, so it's a little tough. But come next week, I should be out of Tucson for a little while, but I'll be available online for sure, and it'll be awesome. So thank you.